Oh, hey guys. So let me get everything set up and go into the slideshow. Right. All right. So, hello. I'm Jacob. I am an engineer at Modular. Kind of one of the long timers here. I've been here, kind of like since we were like a handful of people in a room, and I primarily work on our API and SDK team. So primarily today we're actually not going to be talking about Mojo. I'm going to be primarily focusing on the Python side of things and focusing on kind of like introducing and motivating kind of a new API that we've recently pushed out that we'd love for you guys to take a look at and just let us know what you think. So we're going to primarily talk about the driver API, of course, with a little bit of like engine API side kind of sprinkled in. So the motivation here, kind of in order to like really set the stage, is that we have like LLMs and all these like big models are very memory intensive, right? So we often need like finer grained control over like memory allocation, like data transfer, in order to keep like the our accelerators really humming. And also there are we have situations where we have optimizations like KV caches that can really only be work if we can like within the context of GPUs, if we can keep the tensors backing some of these caches, like to device resident. Otherwise we're incurring like round trip copies between like host and device, and we have issues around that. And then additionally, like we have further situations where like, we might want to have like advanced strategies such as like, specifying like, certain like subgraphs of the larger graph to be run to other devices, and, just to be able to like better orchestrate that and have just, more efficient throughput throughout the entire graph. So kind of with that, now that we're like, thinking about and moving into the grand universe of GPUs, we kind of brought up this driver API. So driver specifically is Python and Mojo API and we're primarily going to be focusing on the Python API today. There is a large amount of offerings on the Mojo side as well. So super happy to drop docs for that and everything. And what driver provides and does is it provides an interface specifically right now primarily for two things, right? So firstly, essentially, it provides an interface around modeling and interacting with devices. So the primary thing that we support right now is essentially allocating memory on those devices and exposing that memory to end users as tensors, right? So with tensors specifically, we support, I'll get into like the feature set in the next slide, but we'll be talking a lot about kind of like how like the tensors and how like do various pieces of conversion between our tensors and like other available tensor libraries. So some of the core functionality here, right? Like one of the really our vision with the device side is to essentially provide a unified interface for interacting with things like CPUs and GPUs. Right now we primarily provide on the GPU side, we're primarily providing like NVIDIA support. We're hoping to expand that out to like other like types of GPUs as we move forward, but like right now the focus is currently on NVIDIA. And it allows for and I'll kind of demo some ways where that at least in nightly packages you can essentially use this device abstraction in order to compile models specifically for a specific device on your computer, and also allocate tensors on those devices. And then on the tensor side, we support like some basic like slicing and like data manipulation capabilities. We support like copies between devices and also I think probably most interestingly like zero copy conversion between like other like Python tensor libraries. So kind of to get into the tensor side of things, right? So, here's like a very basic example of like, actually creating a tensor, right? So the API was designed like, specifically to be fairly analogous to like tensor libraries that we already know and love, such as like, NumPy was a big inspiration, something that we tried to like, keep pretty consistent with, as well as like a torch. So, basically here we're just allocating a, tensor just of zeros, and we have the ability to like set items, etc., take slices, relatively straightforward things, right? So the kind of more interesting thing comes in situations where where, we have situations like, for example, like NumPy itself can add support, right? So in this case, we want to, let's say, create a tensor that is just going to be allocated upon like a GPU itself. So in this case, we initialize essentially like, a CPU device. So we have like some support. Basically, this is just going to, just be an abstraction on top of the CPU itself. We're hoping to expand this to like allow to specify like individual NUMA domains via IDs, but for now, just like, we just have like the single tuple of CPU. CUDA device itself, so this is essentially just like initializing the runtime and like interaction points with a CUDA GPU. You can also provide IDs, and if you have multiple of these devices available. And so then we basically allocate, a tensor directly onto the GPU. We have the ability to also like copy it back to the device, basic things like this, right? So, okay, great. So like some basic functionality here, right? But, let's just say that you don't like, you really don't like, what we have, the API right now is like still very nascent. We don't have a lot of functionality that like, we have in other richer libraries such as NumPy. And let's say I really just want to use NumPy, right? And it's like, okay, that's fine. Like you can do that. So here we do have the ability to support zero copy conversions to and from NumPy. We have like, some first class conversion capabilities from like, NumPy arrays. And we additionally have like first class support for memory map tensors in NumPy as well. So, basically we just, provide simple like, from NumPy methods that allow for you to just create these tensors directly from these arrays. This operation is actually zero copy. So if you essentially make changes to like, the underlying NumPy array, it'll be reflected upon the tensor itself, right? So additionally, the API outside just like, NumPy interoperability provides like generalized interop between a variety of, popular tensor libraries. So basically we do this by using kind of like this like DLPack API that's implemented by most major tensor libs. And so, in the case, so you really can just, if you already have like, a tensor library that you like interacting with, right, you can just use this from DLPack in order to perform a zero copy conversion, right? So here's essentially an example using Torch, right? Kind of similar to what we do in NumPy. And in this case, it's just using the from DLPack, like interface in order to just be able to directly create this tensor. And it is using the same underlying storage, no copies needed. Great. Okay, so, like a lot of this is, it's like, okay, cool, great. You guys have like, some tensors that you can interact with, right? But like let's talk about what the bigger picture looks like, when kind of taking all the APIs that we've introduced and talked about in the past couple of weeks, right? So let's say that what we're going to actually do is we are going to use the Graph API to create a very simple graph like that does a single op that just takes in two one-dimensional tensors that have 5 elements each, and it's going to add them together, right? And it's going to do this directly on a GPU. So in this case, we're going to start off with essentially defining the input types using the Graph API. So in this case, we're going to say that we are going to define a basic input type that's going to be an integral tensor, 5 elements, 1 dimension. We're going to provide 2 separate inputs. So in this case, inputs that the inputs are just going to be like, 2 like of these like, range tensors, basically 1 to 5 and then 6 to 10. And then we're just gonna add them together, and then we expect kind of like the same tensor to be output. So now what we can do with driver is essentially like, we've shown that we can initialize kind of these CPU and like CUDA devices. But now what we can actually do is we can take one of our Max engine sessions and just tell our engine like, please go around the GPU. And so what this will do is essentially like every time that we're essentially loading a model by this inference session, it will essentially eagerly try to compile as many ops as possible and schedule as many ops as possible on the basically the specified device itself. So now let's kind of like so we have like kind of the inference session set up. We have some of the inputs and like input types set up. So now we can essentially kind of use our Graph API in order to define like this graph specifically. So we're just going to take, define this graph right here. Very simple. We just say, okay, please output the result of adding in these two inputs together. And then we can essentially just have kind of like, take all this and just, execute it directly on the GPU, right? So here we actually have, we specifically highlight that, we copy the inputs over to the desired device that we're executing on. This actually is not always necessary, right? So in the case that let's say you have a CUDA you have a torch tensor that's already resident on a GPU. In this case, you don't actually need to perform this copy at all. This copy is actually going to be a no-op, in fact. And I think that we're also experimenting with having our execution API also perform copy, automatically perform copies of inputs if they're not resident on the same device, just to allow for users to keep, users from shooting themselves in the foot. But basically here, we take in these two, so we essentially load the graph, the defined graph directly onto the device. We compile it, then we actually execute the output, the compiled graph on the device with the inputs resident on the device itself. The output itself is also going to be resident on the device, and so we just have to copy it back to the device and then copy it back to the host, and then just assert that everything's equal. So very simple, basically allows for you the kind of interface that allows for you to use, a lot of operations that you would specifically have to use CUDA for without ever having to touch the CUDA side of things, right? So yeah, so basically that's really what we have. Please take a look at it. I'll also include some of our docs in Discord in our Zoom chat. Feel free to raise issues on the Max GitHub repo, leave any thoughts, on Discord as well. Some of the features that, we talked about are actually going to be released for our next release, but are live and nightly. So, if you do want to try out some of these things, do try out the nightly package and, just let us know what you think. So yeah, that's all for me.
Awesome. We have a couple of minutes for questions, if there are any questions from the group. Bueller, no? Okay. All right, well, in that case, we will get right into the magic Q&A. Let me share my screen. And Zach, do you want to introduce yourself for anyone who hasn't met you virtually?
Yeah, I'm Zac Bowling. I'm the TL on all things Magic, but also the former modular CLI that I think a lot of people are used to in the past. But I am been at Modular about year and a half now, and been focused on these problems of how people basically consume Mojo and Max and how they work with it, deploy it, and inevitably work within an ecosystem of people that are also trying to work on Mojo and Max together. And so, yeah, that's basically what I've been doing.
Awesome, thank you. So for context, we have a bunch of questions that community members have submitted over the past week or so, and we're going to get into those. But if you have questions that are just coming to you now, feel free to put them in the chat, and if we have time, we'll also get to those at the end. So the first 4 or so questions are basically different iterations of the same question, which is, how and when are we going to support community package distribution? And the answer to that is a little bit complicated. We're really excited about the idea of opening up this door to a whole ecosystem of community modular packages. And the short answer is that we're really still trying to figure out the best way to do that is both scalable and trustworthy. So we want to make sure that we can have some automation in this so that we can really have a full humongous community, but we also want to prioritize safety and trust. And we're really looking for ways to collaborate with the Pixi developer team to build a kind of trusted means of establishing this ecosystem and distributing community packages. And we know that the community has already taken some awesome steps forward with creating the prefix.dev Mojo community channel. And this is amazing. This is exactly the type of thing we want to see and we want to help support because we really exist in a larger developer and AI ecosystem and we want to embrace that. So that's kind of the TLDR is we're still working on it. We hear you. We can tell by the fact that there's 4 or 5 questions all asking this, that this is definitely something people want. And we're trying to figure out the best way to do that. We'd love to hear thoughts from the community too. If you have ideas on how to do this or you want to get involved, definitely shoot me a DM on Discord.
Yeah. I can elaborate a little bit there on, as I think some of the questions they talk about, I think a lot of people they bring up PyPI, PyPI. And if you think back for what people are looking for when they go to that, they're looking for a place to find Python APIs. And so what's the equivalent for at least the Mojo world? But then we also get people that come to us and they're wondering, how can I just use things on Mac? So we've got things like builds.max or build.modular.com to use pipelines. But just generically, if you think back to what Mojo is, how it fits within the ecosystem, it's people go to PyPI to get Python APIs, but then a lot of people that are in the Mojo ecosystem, they're building on top of Mojo, they're building on top of other third-party libraries, they're building pipelines. So it's a complex sort of question. And we want to solve these like build and package answers in a coherent way that makes sense for all these different use cases. And part of that, I know a lot of people are thinking about Conda and thinking about that level. There's that story. And if you think about this as kind of a layer cake, the Conda ecosystem, the tools that we're building definitely can assist with where Mojo is, where Max is today, with helping solve some of those problems, especially if you're a library developer, because you have a different set of concerns than, say, somebody that's building a project locally and wants to deploy maybe that, or maybe just run it locally and they have runtime concerns locally. So all of this is sort of coming together quickly. I was actually sort of surprised how quickly a lot of our community jumped immediately to that next step of, okay, cool, this is great. Now, how can I use it to build my thing and deploy it within our own ecosystem? And it's been amazing to see how fast the community sort of jumped onto that problem set. But it is definitely one we want to think about and how we can solve, because more than just Mojo, and Mojo has its own set of concerns because it is sort of a new language. We don't want to bind it, 1, to source compatibility, but 2, ABI compatibility. There are tools we can use at our level, but also that doesn't preclude in the future Mojo itself worrying about some of these same problems of like portability and what does it mean? What is this Mojo package format that exists, and how does that become something that you can wrap in a Conda package, or maybe future things of how we can support in a Mojo level specifically different packaging concepts. So it's a big complex question, but we definitely want to figure out a way to fix all this.
Given it's so complicated, is there anything that folks who care about it can do to help?
Yeah, I think part of this is we want to, at least in the short term, because we do have tools. We have a huge set of powerful tools kind of building into an ecosystem that exists with a Conda ecosystem, that we can build packages that say target a nightly, target the current version, even target older versions. If you have your libraries, the same way this works in the Python ecosystem, people build wheels that build for different versions of Python. That can exist while we still have all this. I think part of this is the tools exist in the ecosystem. They're not well documented, especially in our workflows. We can work with the community to sort of come up with a great solution around some of that. We have some ideas, but I think this can be a great collaborative effort that we can have with the community to help support everybody. And because everything is technically possible, I think it's just a matter of we just need to come up with some best practices and some examples to show the community. And then that can help drive sort of future development and our work with Pixi and Upstream, because they're also thinking about this. This is not just a modular thing. The whole ecosystem sort of thinking about the same problem. So yeah, definitely.
Yeah, and if you'd like to get more involved with this, just ping us in Discord in the Magic channel. So we have a couple more questions. So this one from Mohammed, managing multiple projects with various Mojo nightlies is tedious. How can we maintain one global Mojo nightly installation with magic similar to the Pixi command, Pixi global install package name, which can be upgraded for all packages with one Pixi global upgrade package name command?
This is an interesting one. I think one of the things, so this might be more of a uh, niche issue, I want to say, of people that are following nightlies more often. If you think about, so your code is a unit of, it has an environment, has certain dependencies, and what a lot of magic tries to solve is this reproducibility problem of making sure that your environment is exactly what it was with lock files and everything. So global installs sort of break that. And so you think about like the Pixi global install or Magic global install, that tool is not necessarily for library dependencies. It's more for system-wide tooling. So say you want to install Apache, because that's actually in Conda Forge. You can do Magic global install Apache, it will install an Apache that's system-wide. But that doesn't make sense when you're thinking about your code and when it links. And so if you're depending on a specific version of Mojo, that gets a little hairy. But so here's an option. If you're one of these library developers, say you have a ton of projects, you don't have to specify an upper bound on your, say, the nightly version that you're tagging. You could just say greater than or equal to, and then behind the scenes, Magic will cache one instance of it. So the minute you go into each one of your projects and run your code, it assuming you touch the file or do a Magic update, it will, all of your projects will touch each other. It might be something you might have to automate across if you have multiple projects. I think typically most people are going to be working with one or two, not a lot of different projects. But if they do have a lot of projects, usually those are going to be pinned on a specific version, maybe a stable, because it represents sort of a running environment of something. So I think this might be a use case that's not super typical, but if a lot of people are having this issue, let us know. We can see what we can do to maybe optimize for this use case a little bit more. But I think this is one that I think our hardcore sort of library developers are going to run into more than a lot of typical users are going to run into. I don't know. Does that
Next
help?
one is from Anonymous. Host and build dependencies may not play well with PyPy dependencies. If we absolutely must, what are some of the landmines and what are some of the ways to mitigate or circumvent the issues?
Yeah, this is a fun, complex sort of thing. So Magic and Pixi and some other package managers, they sit sort of the crux of two different ecosystems of packages, the Conda ecosystem and the PyPI ecosystem as well. And we support in Magic polling dependencies from either one. That doesn't mean there are usually the same package in both. You can find PyTorch in both. You can find a lot of very popular Python libraries, NumPy, are in both. Typically they will work okay together, but there are some edge cases, and I've run into those. It's hard to document all the edge cases you'll run into. One of those will be BLAST libraries. They'll dynamically link a BLAST library, like Intel's Accelerator 1 and 1, but they'll statically link with the package in the other, and then you run into DLL hell essentially. My best practice is like pick one or the other. You can, in some cases, mix and match a little bit. But for the most part, stick with one side or the other for most of your dependencies when you're declaring them. If you're pulling Python ecosystem packages, if it's outside of the Python ecosystem, of course, go get it from Conda Forge, get it from the Conda ecosystem. But if you're pulling Python dependencies, you're just gonna have a nicer time if you're picking one or the other. You're not gonna have this DLL hell that you'll run into with occasional things. And it does turn out, I prefer Conda Forge based dependencies just because I like that ecosystem. I work with them upstream, but that's not always gonna be great. There are certain packages that just don't have great Conda Forge equivalents. Or it might be that maybe, say you're building for 3 different architectures, the 3 that we support, like Linux, x86, ARM, and Mac. ARM doesn't always get a lot of love, so you might not find an ARM variant in one of the 2 ecosystems, so you're forced to use the other ecosystem to get that package. In those cases, it's one of those that's sort of a hairy edge case, but my best guidance is pick one ecosystem or the other for your Python ecosystem for the most part, and you'll generally avoid these issues. If you run into any specific ones, ping it on the Discord channel, might have a solution there. Someone from the ecosystem probably has ran into it as well. But we can also work with like Conda Forge upstream. We can work with some of these package maintainers upstream if they're missing something. But hopefully these won't be long-term issues as the ecosystem kind of grows and people are supporting more architectures. It's definitely the case with PyTorch in the old days. They didn't release ARM versions for like 2.2, 2.3, but then they did in 2.4. So it's getting better.
Yeah, makes sense. Couple more. If we have our .mojo package in our Git repo, how does one add the Git repo dependency from Magic, and what is the appropriate location / method / process for ensuring that it gets pulled correctly for others?
Yeah, I think this is one we haven't documented very well what Mojo project is. You see this somewhat in the documentation around like the standard library open sourcing effort. So if you think about Mojo project, it is a binary format. It's kind of like a dilib. It essentially is a dilib in a lot of ways, but it is an architectural dependent binary format that is ABI stable with only one version of Mojo or Max. So I wouldn't check this into your Git repo if I was you. Now that being said, for say a package developer or library developer within our ecosystem, you're building your own libraries that you use within your own project, or maybe you're trying to distribute them. You have two options. You have source-based distribution methods, and I think a lot of our ecosystem has done that in the past. But you could, in theory, and we probably need to document this more, you could wrap a Mojo project in a Conda package, tag its dependencies to a specific version of Mojo or Max, do some CI magic to build it for the different architectures. And that is one way to distribute or sort of store these rather than putting them in your Git repo. You could, in theory, like stick them all side by side. I would avoid it. So on referencing a Git dependency, that is also an option that you can do inside of your dependency declarations inside of your project. But I would, in this case, either leave it source, or it's a much longer, harder path, and hopefully we'll put some more documentation and work with the community on this, on how you can wrap Mojo packages inside of Conda packages. Now down the line, this doesn't preclude the Mojo team working on this to have portable, like no arc in the Python ecosystem type packages or source compatibility, but we also don't want to bind the Mojo ecosystem because it's a fast iterating early language. And so I think Mojo package for now will be probably pinned to specific architectures and versions of Max. So keep that in mind. If I would just avoid putting them in your Git repo for now.
Yeah, so I mean, they're just inside of these things. There's a whole bunch of different like implementation details that all get exposed, and so it's an important part of the software architecture of how the compiler works. But we're actively changing that.
Cool. There is a problem with SSL certificates in Magic 0.3 on Mac. This happens in the latest OS, Sequoia, and the previous one. What's the best way to report these?
Yeah, we ran into this one. I think this is one of the ones that we're also seeing an upstream at 2 levels of upstream. So this was a change that occurred within sort of the ecosystem, and I'll give you sort of the behind the scenes. So we build a lot of stuff on Pixi. Within Pixi, it builds upon 2 other major open source projects. One's called UV from the Astral developers, the same people that make Rough. They're great guys. But the UV backend is what we use for the PyPI backend to talk to the PyPI ecosystem to pull packages down natively. They recently had switched their SSL libraries from using OpenSSL to Rust TLS, a pure native Rust implementation of TLS. There is some regressions with that we're noticing downstream. So it's kind of being worked on at 2 levels. I'm debugging it as well to sort of solve these problems. A short-term solution is you can actually use Magic self update -- version 0.2.3. You can go back 1 version, and that will use the older OpenSSL. I have a hunch what's going on here. If you're still running into these problems, you can always go to the Discord, communicate with us. I think there is an open bug also on the Max repo. We're tracking this as well. But hopefully we get this solved pretty quickly so that we don't run into this. And well, we'll definitely have some regression tests soon so that we don't ever have this problem ever again in the future. I think at a few levels, people are adding regression tests for this specific thing. But hopefully we get this one ironed out pretty quickly.
Awesome. This one is long, so it's 2 slides. So
yeah.
Background. The documentation says, by default, this creates a configuration file called pixi.toml, but you can also create a pyproject.toml or mojoproject.toml file for enhanced Python and Mojo project features, respectively. And later, the docs say, currently, these files behave the same, but the mojoproject.toml file allows us to add support for Mojo-specific features in the future. Can I create a default project and then add Max and/or Python? What are the enhanced project features, respectively? If I start a project with pixi.toml, even though it's simply text files, will it break something if I convert it to mojoproject.toml later? If I have a mixed language project, which should I use? Is there any drawback to always using mojoproject.toml all the time? A lot of questions.
Yeah, this is definitely an interesting one. So kind of stepping back, so we have pixi.toml and we have mojoproject.toml and we also support pyproject.toml, and pyproject.toml is specified by the Python ecosystem. But if you think about what these things are, they are files that set up your projects, like metadata of what it's going to build, but also they list a set of dependencies. And so you can have a set of dependencies that are, say, your runtime environment dependencies. And that's kind of what the pixi.toml, it's a language neutral runtime dependency declaration format. But you might have dependencies that are build time dependencies or deployment time dependencies. You could also have additional metadata, and you see this with the Py project, about your entry points. So what are your Python entry points and what are your expected outputs? So the pixi.toml is neutral to all languages, so it doesn't care about inputs or outputs. It only cares about listing the dependencies that are required for your environment to run. Whereas Mojo project and Py project can get a lot more specific in the future, because right now we don't do a lot with Mojo project at the moment, but there are some ideas around the way that might look. But they can declare those things around what are your inputs, what are your test entry points, what are your CLI entry points, what's your deployment look like eventually when we look at how you bundle up what you're running and run it in some environment. And so right now it's very much centered around, you have a set of code with a project that is mostly one language if you're using Mojo project or pyproject.toml. Although Mojo depends on a lot of Python, so you could mix some Python in there too. But it declares sort of that extra metadata more than just the dependencies of running your environment. Now, there's nothing wrong. You could through the task system do everything manually. You just define tasks, like a task for build, a task for, say, a link or deploy, and do it just in pure project or pixi.toml if you want to. And if you have like a complex sort of thing that you're building with multiple languages and everything, that might be the right way to go about it, but you're going to kind of go it alone and build some of the stuff in the future. Whereas Mojo project could inform, say, the Visual Code or Visual Studio extension, what you're doing, and that can automatically wire up your LSP. It could inform like other tools in the future. You already see this in the Py project ecosystem. There's analogies of how it informs IDEs, other tools, but also informs the packaging tool. When you get to the packaging step that says, I want to deploy this as a wheel, what are my entry points? Can I be a CLI tool? And it can specify those. So in the future, not there yet, but we wanted to at least lay the foundation, this format, so that people get in the habit of using it, but there's no extra tooling. So today, pixi.toml and mojoproject.toml, because we're only specifying runtime dependencies, they're 99% compatible. There's like one silly difference right now, but in the future they'll diverge, and we'll have a different set of extra settings specifically for Mojo that we'll go into, that may inform other tools. Still TBD, we're very, very early. So, but we wanted to sort of set that up first.
Great. There is a question in the chat, and that's the end of the questions that we got beforehand. The question is, will Mojo package ever be stable in the future when Mojo is stable, such that given the same major Mojo versions in 2 machines, we can share the packages between them even for minor patch versions, or be stable enough to architectures like x86, 64, ARM64, etc. And also, what's the goal with .mojo package right now?
I might leave that for someone on the Mojo team, because I don't want to say their plans, but I don't think anything is set in stone, and I will say that. We're definitely very early with Mojo, and so right now nothing's a guaranteed contract at the moment on the way this could work. I think this is good input, but if there's somebody on the Mojo team that wants to speak to this, I'd be happy to defer.
I'm sorry, I missed part of the question. Is this whether Mojo package will be stable?
Or portable to multiple
Oh.
architectures.
Yeah, so the answer is yes. The IR within it is portable across architectures. And so this is one of the very fancy things about the Mojo compiler, by the way, is that it generates IR before instantiating the templates. It's a process we call elaboration. And so it keeps the IR before all that target specific stuff gets burned into the code. And so you think of it as, if you're familiar with C, it's like keeping the if-defs in the IR is an overly simplified way. And this is how the whole parameter system ties into things. And there's a whole bunch of really cool stuff. And so the answer is yes, Mojo package does capture that target independent representation. And so you can think of it kind of analogously to like Java bytecode in a sense. And so the answer is yes. The flip side of it, though, is that it is really highly exposed to the internal implementation details of Mojo. And so, like Zac was saying before, as versions of Mojo changes, for example, if somebody renames some operation in MLIR, for example, then the contents of the Mojo package will be broken. And so I would look at it more like it's kind of, it really is tied into the implementation of the compiler, but it's not tied into the architecture that you're targeting from. So over time, I think we can look at this. We could look at stabilizing this somehow. We can look at different designs. It's definitely possible to do, but I think that right now, as Zach's saying, that we really want to get Mojo architecturally set up, right? There's also, just to share, there's also a bunch of other discussions about other things we'd like to do. For example, having more of a compiler server design where the LLVM part of this is out of process. And if the LLVM part of this was out of process, that'd bring your own LLVM much easier. And there's a whole bunch of cool stuff we'd like to be able to do. It's really about planning and execution and implementing all this stuff.
Thank you. 2 more questions. Will Magic have a build everything you can from source for this exact hardware option? I know some options for C, C++, Rust may be more difficult to integrate, but since a lot of libraries do compile time feature detection for things like SIMD ISAs, they may need to recompile to get full performance.
Yeah, this is an interesting one. I think the Conda ecosystem is definitely a binary distribution platform by default. PyPI can be both. You can have SDist wheels. You can also have binary wheels in that ecosystem. And one thing you can do in Conda packages is that they can actually store the recipe that was used to compile them internally. So there is a way to, in some cases, rebuild things. But rebuild world sort of thing is definitely one I don't think too many package managers have pushed too hard on, at least in the Conda ecosystem. In the Python ecosystem, to a little bit. You see it with like embedded Python sort of ecosystem does it to some extent. But it's an interesting concept. I think definitely not one that I don't think any of the tooling in the ecosystem is optimized for yet. It's not like Gen 2. If you think of a Gen 2, it was rebuild everything with the most like strict or the most optimized compiler flags every time. But I think one thing we can do is we can, at least for our packages, we could publish more architecture ones. We actually did this in the modular CLI days. We actually had like an AVX 512 build of everything, but we moved away from it because we saw that we could JIT more at runtime that was more optimized for an architecture rather than just like provide binaries for every single microarchitecture that existed. And so we moved away from that in the modular CLI days, like back in the 0.4 days, 0.5 days. And in 0.6 Mojo, we just started shipping like, here's a generic x86 because we could do those optimizations at runtime. And so there was less of a push, I think, for that. And I think we could do that for some things. It's hard to say this for all your dependencies that you have within the ecosystem. Say you're depending on PyTorch. They provide some architecture, microarchitecture optimized builds, but not in like their main channels, because they're mostly focused on GPU and CUDA. And so they don't do that so much for CPU, but yeah, it's an interesting concept. Also, I'll put it at that.
Cool. Thank you. I think that's all the questions that there were. Thank you, Zac, and thank you, Chris. With that, I'm going to hand it over to Maxim.
Thank you very much. Hello, everybody. I will start sharing my screen in a second. Here we go. You should be able to see my screen, I guess, currently. Yeah, cool, great. And I'm going full mode, and I can see folks anymore. Okay, so welcome everyone. My name is Maxim, and I would like to talk about what it takes to uppercase a string in general and in Mojo. So when we talk about uppercasing a string, we can think about it in a very easy way. We say we have an A, and we would like to make it a capital A, right? And currently in standard library, we have also a really nice way how we can do it, because like it only supports ASCII, and in ASCII we just need to flip the 6-bit, which is super nice, easy, just 2 operations, 1 line of code, everything is great, right? Problem is we have a little bit more characters which we support generally in the world. So we have this kind of characters, or this kind of characters, or this kind of characters, and they all have uppercase cases, right? So generally we would like to support Unicode, and Unicode reflects a little bit more of 30,000 characters in its base database. What is the Unicode database? Well, generally, if you go to Unicode is an organization, and if you go to this URL, you will just see the Unicode database, which is just a bunch of text files, which are structured kind of like CSV files. And one of the important one is this Unicode data.txt file, which looks something like this, and it is, as I said, it kind of like CSV. It's semicolon separated, not comma separated, but generally it's quite parsable in a way. And here we see we have columns for every character that it supports. As I mentioned before, a little bit over 40,000 of them. And if we are interested in what the columns mean, we have this website where we have this kind of table, which basically says like, okay, in the column 12, we have uppercase mapping, in 13, we have lowercase mapping, and in 14, we have a title case mapping. Fun fact, uppercase mapping and title case mapping can be different, but most of the time we are interested in the uppercase and not this specific title case. Right, so if we look into this base data.txt, we can find 1,450 characters which have mappings to uppercase. But that's not all. Actually, there is another file called special casing txt. Sure, there are always special cases. And what does it entail? It entails cases like, for example, what you see here is of German character SZ or sharp S, which when you uppercase this one, you need to create write 2 upper S characters. Although there is actually also an uppercase SZ character in Unicode, but the convention is to translate it like this. And if you want to go with convention, we need to do this kind of stuff. Also, for example, this kind of character translates in uppercase to this character. And if you think, okay, I don't care, I only write English, well, in English, you can also have so-called ligatures. Ligatures are cases where you would like to write two characters nicely as one, when it looks nicer. But again, when you want to uppercase them, then you would have to write them as two characters and not just as one character. So in total, there are 39 cases in this special casing file, which are locally independent. And then, sorry for that. And then there are also a few cases specific to Lithuanian, Turkish, and Azeri. So basically, if you want to have like complete support for Unicode uppercasing, you also need to check the locale if you are your user is in Lithuanian, Turkish, or Azeri language. Then you have still special cases. Okay, so how do we implement casing in Mojo? Well, generally we have two options. We can create a lookup table based on the database, or we can write conversions logic by hand. In April, I was on vacation and probably a little bit bored, so I decided to actually write them by hand, but only for lowercase. While lowercase don't, almost has no special casings, so I could just take the base data file. Then I wrote a script in Mojo to generate a CSV for just lowercase conversions. So it's kind of nicer to see with following columns. And then basically I eyeballed it and wrote kind of a decision tree how we can just check which character needs to be, which uppercase character should be transformed into a lowercase character. So lessons learned, very tedious work, took me a couple of days, basically a couple of hours a day, and it ended up being like about 500 lines of code, but it was quite easy to validate because basically we already have this table, and to validate, you just go through the table and check if every conversion actually works, right? So like a unit test is quite simple, and you can see like if some conversions are wrong. Another thing, we actually in Mojo, our strings are UTF-8 encoded. In the table, we actually talk about code points, which are 4-byte long. And this is why also when I created a table, I created columns to see how these characters will look like as UTF-8 bytes. So the first decision I did was actually by character. As we saw before, 1-byte character is ASCII, and for this, the conversion rule is quite simple. For 2-byte characters, there is certain decision to make. 3.4 is actually different. So the first decision is actually to see, okay, how many bytes does this character which we want to convert entails. Okay, so one more thing which I wanted to mention from lessons learned is actually quite interesting for 2-byte characters which are uppercase. It sometimes happens that the conversion to lower character is not 2 bytes, but 1 or 3 bytes long. This also means that we can do the conversions just in place. Like first I thought about, oh, maybe we could just directly reuse the memory and say just to lowercase and just in place convert the chars, but it's not possible because they are actually, the resulting chars might occupy more or less bytes than what you have in source. Okay, few weeks ago, I tried the lookup approach. I also created this PR 3496, where what I say is basically I generate the two lists basically, right? The list is uint32, so it's the code point value from the string, and I say, okay, I have one list where I say those code points have lowercase mapping, and then another one where I say, okay, lowercase mapping is following value. What I do then, I do the binary search on the has lowercase mapping to find the index. And then if index is -1, then do nothing, or rather actually keep the same character that you have already in your string. Otherwise, look up the value in the lowercase mapping by index, and then convert it to a UTF-8 string by calling the char function. All right, so lessons learned. This is quite easy to implement and keep updated, and also to understand than what I wrote by hand. We have a fixed memory overhead. We have like 1,433 characters which can be lowercase. Then we have two tables to list, and each list is of 4 bytes, so it's almost 12 kilobytes which we have on overhead when we want to convert, which is kind of okay, not that bad. But the main problem is it's actually slower than the handwritten version. You might ask how much slower? Well, I measured it on M1, and I have like multiple tests. One test where I just go through, I have a list of all uppercase characters which can be lowercase. And in this case, in this test, actually lookup is 20 times slower. I have an example where I have a text in Cyrillic, which is about 3.2 kilobyte long. Then we're at 2 times slower, and I have a German text, which is almost 5 kilobyte long, and this is 5 times slower. This is an interesting result, so I thought like, okay, maybe I could speed it up somehow a little bit. So what my idea was to say like, okay, maybe let's try if we can have like multiple small lookups. So, and they are UTF-8 based, similar what I did in the handwritten version, where I say, okay, I don't have to call ord and char anymore because I have like table per character bytes. So in this case, we also don't need to have a lookup table for ASCII because there the transition is trivial. And we have then separate lookup tables which have like 443 elements of uint16 for 2 bytes, which results in this size in bytes, then for 3 bytes and for 4 bytes, right? And then I try to benchmark it again. What I see here is weird in a way, right? So like the test for every character in a list is even slower. But when we look at the actually text, where we don't have, with the text, we have some capitalized characters, but not all of them. In this case, we're actually almost the same as the handwritten algorithm, right? Which is an interesting result, in my opinion. Another idea which I had to say like, okay, maybe I can speed up the index lookup even further, because I've thought it's maybe like index lookup is the one thing which is most expensive. I am currently not sure anymore, but let's talk about it a little bit later. So what I did is basically, I told you that to look up the index, I use the binary search. And this is kind of like a binary search, which we all know and love, I guess. Typical like low, high. We have a while low smaller than high. We do stuff, we find something, we return, right? I guess everyone is familiar with this implementation of binary search. But there are actually also other more efficient implementations of binary search taken from this book, algorithmica.org. It's open source. You can actually freely read it. And here, the author presented a branchless binary search, which looks as following. It's much simpler, right? In the caveat is basically what you see here. In the while loop, we don't have any branches. We go always to the lower level of a binary search tree, if you think about like an erased binary search tree, right? And then when I implemented this, I thought like, okay, actually, as our lookup is static and known at compile time, the depth of lookup is actually also static, and we can compute it at compile time as well. So I created also an unrolled version. This is just a stupid way of computing the log2 for an and the interesting part is basically here where we say like, okay, we have this search function where we do these three statements to find the cursor, and then we just unroll it to the depth of the lookup. Okay. Third version which I implemented is again from this book. I guess you folks probably familiar with data structure, which a B+ tree, and in this book the author also explained how one can create a static B+ tree. I'll try to explain it briefly. So imagine you have this sequence of numbers from 1 to 17, and you would like to create a B+ tree out of it, where every node has four elements in it. When we create the static B+ tree, this is the resulting array. So we keep this one. So this is just one mem copy, and then we add here. This is basically padding with the highest number which we have here. And then those are, this is actually the parent node. So here, this is a proper logical representation, how it is then used in the algorithm. Basically, we have, this is the parent node, and those are the children nodes here, right? And basically, if the number we're looking for is smaller than 5, when we go here, smaller than 9 here, smaller than 13 here, smaller than 17 here, and if it's bigger than 17, we go here. Same thing here, just a little bit more numbers, but I don't have that much time, so I won't go into details, but I think you folks can actually understand how stuff work. And also, please have a look at the book. It's quite interesting, kind of nice. Okay, so now to results. Binary search. Here we have like three arrays which we have with uppercase characters, 2 bytes, 3 bytes, and 4 bytes. And if we do binary search, those are the results. This is like binary search of a default one. When we do branch-free binary search, it's actually a little bit slower. It varies a little bit. Like in this run, it was a little bit slower, but often it's a little bit faster. And I also tested it on M1, I think when I had an Intel machine on Intel, it was actually much faster than this. But if we look at the branch-free unrolled version, this is actually faster than the normally binary search on every version of string. With S3, the static B+3, the results are a little bit, sometimes it's slower, sometimes it's faster, although I must say I chose the number of nodes, elements in the nodes to be 16, which might be not super good for M1. It should be much better for Intel, where we have a 512-bit SIMD registers. Yeah. And on M1, we have only 16 bytes, so it's much small. It's actually, it's not optimal. Right. Well, now let's have a look at the benchmark that I did. Again, now with numbers, we see like convert every uppercase char. Handwritten is 20 times, 30 times, and 28 times faster, which I think actually it's not due to the fact that we look up that the lookup is slow. I think it's actually due to the fact that the data get evicted from cache, because when we first search and then we load again from the lowercase table, and I think what CPU does is basically, because when we convert every character, we actually evict the lookup table out of CPU cache, and then we try it again. So we need to close it again. Again, it's my suspicion, because as you can see here, for example, when we just look through Cyrillic text, where the characters are mostly 2 bytes long, actually UTF-8 lookup here with unrolled branchless binary search is even a little bit faster than hand-rolled, right? And here, when we look through German characters, where most of the characters are just one byte and some of them are 2 bytes, it's kind of comparably the same. All right, the code is on GitHub. I'm done. Thank you very much. I'm a little bit over time, but not that much.
Thank you, Maxim. That was great. There is a question in the chat from Sawyer. Are the characters that have a lowercase substitute clustered in a way that can be exploited? Common bit prefix, etc.
Wait a second, come again. I didn't 100% check the. Could you repeat the question? I didn't.
Yep. Are the characters that have a lowercase substitute clustered in a way that can be exploited? Common bit prefix, etc.
Right. So generally, this is what I did when I was eyeballing the table, right? So like I assume most of the time you can just add, so they're clustered together. So what I did in the hand-rolled one, I actually don't return the lowercase character. I return the vector which you need to subtract from the source bytes, because it's often like, for example, in ASCII it's normally -32. In lots of half a byte characters, it's also either -32 or -17 or whatever. There are actually common pattern for this. So when you do lookup, you don't do this, because like you would like to just find something and get a replacement, but when you write it by hand, you actually can think about like what is the most efficient way how you can characterize the characters, if it's uppercase, lowercase, or and how can you actually translated to lowercase.
Awesome. Sawyer says thumbs up. Any other questions from the group? Okay, well, if there are no other questions, I'm gonna make everybody come off of mute and give the speakers a round of applause because I'm annoying. Don't be shy, just, all come off mute. Okay, nobody's coming up. Thank you, Gary. If you were in person, you would get some applause, so we gotta give you some incentive here. And yeah, thank you so much, everyone, for coming. The recording will be on YouTube hopefully later today, and we'll see you in 3 weeks. And reach out if you want to speak at the next meeting. Bye.